Hi everyone, I just wanted to follow up on the last problem that we were doing in class today. So I realized that I had somehow in my notes mixed up the wrong equilibrium constant for this particular reaction. So this led to a little bit of difficulties in determining the final partial pressure of the reactants and products. Though the process in which we attack the problem is 100% valid, and it's actually the way you should be attacking these problems. But I thought it would be beneficial if I follow up with a mini lecture just on this one particular problem, breaking down the steps that we had already talked about in class, but using a Kc and a temperature that should give us a little bit more realistic values and a true sense of, you know, how these problems should be solved. So let's take a look. So this was the original problem that I had put on the board. So there's a couple things I'm going to change. So as I mentioned in my notes, somehow something got lost along the way, so I wanted to correct this for you. What I ended up doing is I found just a new temperature and new equilibrium constant for this process, the Haber process of reacting nitrogen with hydrogen to make ammonia. So the only difference in the problem is that I've changed the temperature at which the reaction occurs to 600 K, and the equilibrium constant, the Kc, is now 2.25 times 10 to the negative sixth, and that's a unitless constant. So let's attack this. We'll just walk through the same thing that we'd done in class. So as always, I encourage you, as my students, to just write down what's given. It organizes everything from a written paragraph form, word form, problem into something that's a little bit more manageable in terms of variables. So the reaction's happening at 600 Kelvin. Our initial amount of nitrogen is 3.5 moles. Our initial number of moles of hydrogen is 2.7 moles. We have 0 moles of ammonia. So if we think about how that experiment is set up, we have a container, and all we've done is added nitrogen and hydrogen, and then we pause time. We're going to look at what happens when we unpause time in the thought experiment and how that affects the concentration of the reactants and the products. This particular reaction is happening in a volume of 5 liters, and as was reported in the previous slide, our Kc is now 2.25 times 10 to the negative sixth. So we just remind ourselves we're looking at this particular reaction where nitrogen reacts with hydrogen in its equilibrium to form ammonia. Oops, I realize I have one small little typo here. That should be NH3. That's not going to change anything in terms of the coefficients. So when we look at this these expression for the equilibrium constant, again, it's going to be our products over reactants, and then they're appropriately raised to the exponents. And we said only under equilibrium conditions do the exponents correspond to the coefficients in front of the different molecules. The first thing that we did on the board was we realized that, all right, I know the number of moles I have of each individual gas. I know what the volume is that that gas is enclosed in, so I can use that information. So essentially these 3 bits of information here, we'll put that together and we can know the initial concentration in molarity of nitrogen and hydrogen. And we made that initial assumption, which is totally valid, in that the amount of ammonia is at 0 molar, because the system was set up in such a way that we know we had a box or a container that's 5 liters, and we only added nitrogen and hydrogen and no ammonia. So that was our initial concentration. Then we asked the question, well, how is this going to change once it is allowed to establish a new equilibrium? So we know from looking at this initial concentration that we only have reactants. So if there is any sort of Kc at all, some of this reaction at least has to go forward to form ammonia. If I had given you numbers here, here, and then also underneath ammonia, we'd be in a little bit more difficult situation of trying to figure out what direction this reaction would go in to establish a new equilibrium. But what we see from here, we only have reactants. We know an equilibrium needs to be established, so therefore some ammonia has to be produced. So if we look at this, again, we said if we had a certain amount of nitrogen and some of it's consumed, right, it's going to produce some ammonia. And we realize that these X, this amount that's been consumed or amount that's been produced, is proportional to the molar ratio between the products. So we have minus x associated with nitrogen, minus 3x associated with the hydrogen, and plus 2x associated with the ammonia. Then we just add those together, the I and the C, to get our equilibrium concentration. So it just ends up being 0.7 minus x for nitrogen, 0.54 minus 3x for hydrogen, and 0 plus 2x, or equivalently just 2x, for ammonia. So I've just moved that up to the left-hand corner of the screen, and I've rewritten what the expression is for Kc. So again, forgive that little typo over here. I'm reusing screenshots from previous scanned documents that I had, so I can't go in there and change the NH2, but it should be NH3. But we know that this in general is, here's our products raised to the coefficient. There's our 2 times our nitrogen and our hydrogen raised to the third. All we need to do now is we can link this equilibrium concentration here, which is now expressed in terms of x, and we can link that to our equilibrium constant. So in that case, we are just plugging in our variables. So here is our Kc. Here's our concentration of our ammonia raised to the second. Here's our concentration associated with nitrogen, and the concentration associated with hydrogen raised to the third power. So we talked about in class, when we have expressions like this, if we're looking here and just even estimating really quickly, it looks like if we tried to solve for x explicitly, we'd be looking at a fourth order polynomial, which is not easy to solve for. So we need to make some assumptions. And the assumption that we talked about in class, and usually it's a reasonable assumption when attacking equilibrium problems, is to assume that x, so this change here, is very, very small, or much, much less than the concentration of N2 and the concentration of H2, right? So we would say if x was very, very small compared to 0.7, essentially this would all just collapse down to approximately 0.7. And the same thing here. If you're taking this number 0.54 and minusing something very small from it, essentially it's just going to end up being around 0.54. And so that makes our life a lot easier mathematically. So what ends up happening is, because this number up here, it's a real number, right? Even though it's very small, it's non-zero, but so we need to incorporate it into this top part of the expression. But if we have a very, very, very small non-zero number, and we're looking at its difference compared to a large number, that means it's something really, really huge minus something which we're assuming right now to be very small. And that's why we can assume that that part, this number right here within the parentheses, is approximately 0.7. And we're making the same assumption here for the hydrogen, in which the concentration is approximately 0.54. So again, this simplified our math. We'll need to check our assumptions later, but right now we basically have one unknown, one equation. You have one x right here. This becomes pretty simple math. So I've just recopied the equation up here. All I did was take the denominator, move it over to the left-hand side of the equation. Some people ask me about this, where I got 4x squared, but remember, this squared outside the parentheses gets transferred to both numbers. So it's 2 to the second times x to the second. So 2 to the second is 4, x to the second is just x to the second. I've just rearranged it, so I'm just used to solving x's on the left-hand side of the equation, so I've flipped it. You get x squared equals this number, and then you take the square root of both sides and end up with this number 2.490 times 10 to the negative fourth. So I know that has extra sig fig compared to the 3 sig fig that we've had in the other numbers, but right now, I think I mentioned this in class, is because this is an interim operation, so the math is happening somewhere in between what we started with and what we're trying to get to in terms of an answer. We usually tack on a couple of extra significant figures to avoid rounding errors, and we'll apply sig fig in the end. So let's see what happens if we plug x back into the equation. So we just solve for what x is, right? And so far, it's actually looking pretty good, because we assumed x was much, much, much smaller than the actual 0.7, and we see, based on this assumption, it actually seems to hold true, right? 0.7 is really darn close to 0.6998. So it seems to me that we're probably heading in the right direction, though we'll have to double check later. We plug in our x into both equations. We have a final concentration of N2, final concentration of hydrogen, and a final concentration of ammonia. But that's not what the question was asking. The question was asking us to report this in partial pressure. So before we even go and try that, let's just even see if these concentrations make sense. So this was our original expression for Kc, which is the concentration of ammonia squared, over N2 to the first, H2 to the third. And we know that equals 2.25 times 10 to the negative 6. So let's check our assumption. We know what Kc should equal. Let's plug in our values that we calculated here and see if we get the same Kc. So there's our concentration of ammonia, nitrogen, hydrogen. Well, look at that. Our Kc calculated from our assumption is roughly approximately the same excuse me, as the literature value. So this is the literature value we were given. This is the value we calculated with our assumption. That is a reasonable amount of error. So we don't need to go back and try to solve a fourth order polynomial as long as our assumption held true, and it seems to be holding true. So these are pretty valid concentrations of the final equilibrium concentration for nitrogen, hydrogen, and ammonia. But we still have one more thing to do. We still need to solve for partial pressure. So I've just rewritten what our final concentrations are in molarity. If we look to assuming that they behave ideally, these are all small molecules, we can use the ideal gas law. So what I've done here is rearrange it. So N over V is on one side of the equation, and we know the units for N over V are moles per liter, which are the same as molarity. And then I have the right-hand side of the equation, which is now just P over RT. So in the end, the partial pressure of each of these components is just equal to the molarity of the component times R times T. We plug that in, so everything in the red box right now is actually the final answer. I've attached, well, I reported the answer with 4 significant figures. It should be with 3 significant figures. But the partial pressure for each of the components is represented there. We have 34 point, which I guess with 3 sig fig would be 34.5, 26.6, and 0.0245 atmospheres for N2, H2, and NH2 respectively. So again, we can do one more check on this. Sorry, my throat is getting dry today. This is going to introduce a little bit more error because we've done so many mathematical operations and we've applied sig fig a couple of times throughout the example. But a good approximate check, so we've already checked Kc and it works out. We've converted to partial pressure. Let's just round everything off and pull together all of the things that we learned. We know Kp is equal to Kc times RT raised to the delta N. We've already talked about that the delta N of this reaction is -2. The reason for that, if we look up here, it's the number of moles of the balanced chemical equation of the products minus the reactants. So 2 minus 3 minus 1, -2. All we have to do is just insert our values. And so we know here's the Kc that we were given, here's our literature value, here's R. There's our temperature raised to the -2nd. I've omitted units just for the sake of clarity of looking at the numbers. We end up with a Kp of 9.161 times 10 to the -10th. That would be what our theoretical Kp should be based on the Kc. So let's plug in our actual values. So all I've done here is just take the partial pressure of ammonia raised to the 2nd. That's all divided by the partial pressure of nitrogen and hydrogen raised to the 3rd. We plug that all in. We get about a 9.33 times 10 to the -10th. We're comparing that to 9.161 times 10 to the -10th. I already alluded to that we'd have a lot of compounded error based on the fact that we've applied significant figures several times throughout the process. So lots of rounding errors, so being a few decimal places off is acceptable. And if we're looking at in total terms of error, it's only about 2% error, which is pretty reasonable. So in the end, we've solved everything. There's our final answer. Our partial pressure of this reaction, given the concentrations, the Kc, and the temperature, our partial pressures for our components are reported here. All right, I hope that made sense. If we're still having issues, my Monday, Wednesday, Friday class, we're meeting on Friday, so we can address that then. And my Monday, Wednesday class, again, if we're having issues with this, we'll come back and retackle it on Monday. Hope this all made sense, and I will all see you soon. Hopefully we don't have a snow day tomorrow, but if we do, enjoy. I'll see you all later.